All right, one more related rates example, a pretty challenging example. It's another problem with boats, so it might seem like it's similar to the problem that we started this series of videos with, where we had boats that started in the same position, one went north, one went west. We were able to figure out this right triangle and tie together the lengths of the sides of that triangle. I mean, that basic idea is what we're going to do down here, but what's going to make things challenging is the boats don't start out at the same point, and also they don't travel perpendicular to each other. One of the boats is traveling south and the other one is traveling northwest. And that'll end up making things a little bit challenging. But I think if you draw the picture, it's pretty manageable. So what's going on is at the starting point at noon, boat A is 20 miles north of boat B. So I don't know, maybe this is boat A, we call it like A naught or something. And then way down here, 20 miles south is boat B. Call that B naught. And the distance between these boats is 20 miles, I'm guessing. Yeah. What makes this challenging is these boats don't stay stationary. Boat A is traveling south at a rate of 2 miles per hour, and boat B is traveling northwest at a rate of 3 miles per hour. And I'm interested in the distance between these boats 2 hours after the starting period. So if boat A is traveling south at a rate of 2 miles per hour for 2 hours, then boat A has traveled 4 miles. So at 2 p.m., boat A is right here. I don't know, maybe A with a little 2 in the subscript. Unfortunately, boat B isn't just traveling west, boat B is traveling northwest. So kind of taking this path like this, 3 miles per hour for 2 hours, it sounds like boat B has traveled 6 miles and ends up over here at 2 p.m. What I'm interested in is the distance between these boats. So the distance between them starts out as 20 miles because boat A starts out 20 miles north of boat B. But at this instant that I'm interested in, the distance between them is the length of this line segment pictured in green. What the question is asking about is the rate of change of this line segment in green. If I call the length of this line segment, I don't know, little c maybe, c prime is what I'm trying to figure out in this problem. Maybe at this point it makes sense to kind of connect some points and see that we have a triangle hidden in here. The red leg of this triangle, maybe I would call it little a, and it represents the distance that boat A is north of where boat B started. And since boat A started out 20 miles north of boat B, and boat A has been traveling south for 4 miles, right, 2 miles per hour for 2 miles, boat A is currently 16 miles north of where boat B started. And if A represents this length in red, maybe it makes sense to call little b this length in purple. This side length is the distance that boat B has traveled since noon. It's going 3 miles per hour. It's been doing so for 2 hours. Sounds like it's traveled 6 miles. From our picture, we know that A is equal to 16, and we also know A prime, but be a little bit careful here. A prime is the rate at which this side length is changing. Since boat A is traveling south, this side length is getting shorter. How quickly is it getting shorter? Well, it's traveling at 2 miles per hour, so A prime is equal to -2. From our picture, we know that B is equal to 6, and based on the fact that boat B is traveling 3 miles per hour, we know that B prime is just equal to 3. We have this relationship which ties together little a, little b, and little c, but the challenge is it also has a capital C in it, so it almost looks like we have an extra letter floating around in here. But I got some good news for you. Capital C is a constant. Why? Because in this picture, this angle right here remains constant. Boat A is due north of where boat B started, and boat B is traveling northwest. So what that means is this angle is 45 degrees. The way I think about it is if boat B were traveling due west instead of northwest, this angle would have been 90 degrees. But he's not. He's traveling northwest, therefore it's half of 90, aka 45. The version of the law of cosines we'll be interested in is a squared plus b squared minus 2ab cosine of 45 degrees equals c squared. And there's no reason to leave a cosine of 45 degrees in there because the cosine of 45 degrees is the square root of 2 divided by 2. So I could write a squared plus b squared minus 2ab root 2 over 2 equals c squared. In fact, I can even clean this equation up a little bit, canceling out this 2 and this 2 to get a squared plus b squared minus the square root of 2 times ab equals c squared. I think the big challenge in this problem is seeing that capital C is not a function. In fact, it's a constant 45 degrees. And that kind of goes against what I said at the very start of these videos, where I said that everything is a function. I guess that was a little bit of a lie. What I'm saying is you're not going to have any variables floating around in here. Everything is either a function or a constant, when you're setting up these different equations. Anyways, with that out of the way, I think we can solve this problem. In fact, I'd argue that this is a good point to stop the video and see if you can finish it on your own from here. I think there's two big hurdles left. We're going to have to take the derivative of both sides of this equation, and that'll involve implicit differentiation. And due to the complexity of this equation, that won't be especially easy, but I bet you can do it. The other challenge is, after you do all that, I think what you'll find is you need to know A prime, B prime, all things that we know, and also C if we're trying to solve for C prime. And C we don't have written down yet. The good news is we can figure out C from this equation by plugging in our values of A and B. C squared is equal to A squared plus B squared minus the square root of 2 times A times B. And since A is equal to 16 and B is equal to 6, I get 16 squared plus 6 squared minus the square root of 2 times 16 times 6. I can already see these numbers are going to suck. 16 squared is 256, 6 squared is 36, and 16 times 6 is 96. So I get that C squared is equal to 256 plus 36, in other words 292, minus 96 times the square root of 2, whatever that ends up being. But I'm not interested in C squared, I want to know C, so C would be equal to the square root of that mess, 292 minus 96 root 2. Anyways, the good news now is kind of the bad part is out of the way, and all you have left to do is calculus. That might sound like a strange statement, but I think it's going to be a little bit more satisfying taking the derivative of both sides of this equation. On the left side, I have three different terms, so I need to know the derivative of the first term, a squared. I need to know the derivative of the second term, b squared. Then I can view this negative root 2 as a constant and pull that out in front of the derivative of a times b. On the right side, I just need to know the derivative of c squared. Some of these things are harder than others. For the derivative of a squared, think the chain rule. I bring the 2 down in front, I leave the a completely alone, but then I'm not done. I have to multiply that by the derivative of a, which is a prime. Same idea for the derivative of b squared. I end up with 2b prime. But then for this third term, maybe I have to show a little bit more work. I can pull this negative square root of 2 out in front, but then I have to take the derivative of a times b. And for the derivative of a times b, you got to think about the product rule. It's the derivative of a times b plus the derivative of b times a. That whole mess is going to be equal to the derivative of c squared, and much like the derivative of a squared was 2a prime, the derivative of c squared is going to be 2c prime. A little bit more calculus left to do in here. The derivative of a is just a prime, so I got a prime times b inside these parentheses, plus the derivative of b is just b prime, so I got b prime times a as the other term inside these parentheses. That's equal to 2c prime. It looks kind of ugly, but it's easy enough to solve for c prime, which you remember is what we're trying to figure out in this problem. C prime is just going to be equal to 2a prime plus 2b prime minus the square root of 2 times a prime b plus b prime a, all divided by 2 times c. It might not be especially satisfying to do so, but at this point all we got to do is plug in numbers. C prime is equal to 2 times a, which is 16, times a prime, which is negative 2, plus 2 times b, which is 6, times b prime, which is 3, minus the square root of 2 times a prime, which is negative 2, times b, which is 6, plus b prime, which is 3, times a, which is 16. I got to divide that whole mess by 2 times c, and remember c is equal to the square root of 292 minus 96 root 2. All we're left with are numbers here, so I guess in a sense we're done. You could say c prime is this expression, but if you wanted to clean things up a little bit, you could say 2 times 16 times negative 2 is negative 64, and 2 times 6 times 3 is 36. And from that, I want to subtract the square root of 2 times negative 12 plus 48. Negative 12 plus 48 is 36, so I got 36 root 2. And in the denominator, I got 2 times the square root of 292 minus 96 root 2. Clean things up a little bit more by canceling this 2 with a 2 from each of these 3 terms up top. If I take a 2 out of this, I got negative 32. If I take a 2 out of this, I got 18. And negative 32 plus 18 is negative 14. If I take a 2 out of this, I got 18 root 2. And down in the denominator, I'm left with just the square root of 292 minus 96 root 2. Could you simplify this more? Probably. I mean, I think you could pull a 4 out of each of these terms down in the denominator that are underneath the radical, which would make it a 2 outside of the radical, which you could cancel with this stuff. I mean, sure, I guess I could do it. The numerator, I'll pull out a 2 and I'll get negative 7 minus 9 root 2. The denominator, I'll pull out a 4. 292 divided by 4. Well, let's see, 300 divided by 4 would be 75, because 75 cents times 4 is $3. But I don't have 300, I have 292. So instead of getting 75 when I divide it by 4, I only get 73 when I divide it by 4. And if I take 96 and divide it by 4, well, if it was 100 divided by 4, I'd get 25. But it's not. I'm 4 short of 100, so I only get 24. What I'm saying is we can factor out a 4 from each of these terms, which gives us a root 4 outside of the radical, but the square root of 4 is just equal to 2, so this 2 and this 2 cancel. And maybe a prettier form of my answer would be negative 7 minus 9 root 2 divided by the square root of 73 minus 24 root 2. And I guess pretty in this case is in big old air quotes, because this isn't the prettiest thing in the world. But at least the numbers are a little bit smaller than what we had up here. I don't really need you to be able to simplify radicals like I did here. I just figured it never hurts to show you more algebraic tricks. Before we call this good, I want to make a comment about this answer right here. Note that it's a negative number, because the denominator here is positive, because I'm taking the square root of a positive number, and the numerator is negative, because I have a negative minus even more. Wait, why is my answer negative? Does that make any sense? Yeah, we're thinking about the rate of change of c here, the distance between the boats, and the boats are actually getting closer together. They're not getting further apart. The length of line C is getting smaller at this rate. Oh yeah, I can kind of see that, because in a couple of instances, this boat A will be like down here, and boat B will be over here, and the distance between them is slightly less, this line in purple, than the distance was a minute ago, this line in green. The fact that my derivative is negative just means this line is getting shorter, which just means the boats are getting closer and closer together, at this instant anyway. It's a pretty hard problem. The calculus in here is hard. Just drawing the picture is really hard. We've done several really hard examples in these videos, but hopefully I've prepared you for the hardest things that you'll see. And then when you work out homework and quiz problems, everything either looks like something that you've seen in one of these videos, or maybe is a slightly easier version of them.